So let's jump in and do what I consider to be a pretty challenging problem. What if we have the following division? 6 divided by I times the square root of 2, that's a complex number, divided by 6 plus I times the square root of 2, which is another complex number. So the fact that the radicals are here, don't let it bother you. Everything is done the same. It's just that we have to be very careful to tackle the radicals properly. So what we're going to do here is we're going to rewrite everything so we don't clutter up my original drawing. 6 plus I root 2. And then we have to multiply by what? By the conjugate on the numerator and denominator here in order to clear the imaginary numbers out of the bottom. So we're turning the division into multiplication. So it'll be 6 minus I square root of 2. That's the complex conjugate here of the bottom. 6 minus I times the square root of 2. And if we do it right, when we do this multiplication on the bottom, we should have only a real number as an answer on the bottom, and then we'll simplify everything, and then that'll be our complex number as the final result. So you need to think of this as having an invisible parentheses. In fact, let's just do it for this particular problem. We're not going to do it for everything, but just you can always envision these things as having kind of invisible parentheses around them. It helps you visualize the multiplication in some cases. So on the top, we have to do FOIL. 6 times 6 is 36. The inside term, 6 times negative I root 2, is going to be negative 6I root 2. Not much more you can do there other than write it down. Then this 6 times this negative I root 2, again, becomes negative 6 times I times root of 2. Be careful on the last. Negative times negative actually is going to give you a positive. The I times the I will give you I squared, and then the square root of 2 times the square root of 2, we can write it as the square root of 2 times 2, which is 4. So we're taking these roots as we multiply them and bringing them under a common radical. Now that looks ugly. That's the numerator of this fraction. On the denominator, we have to do something similar. 6 times 6 is going to give me 36. The inside, the 6 times the I root 2 is 6I root 2. The outside, 6 times this negative here will give me negative 6 times I times root 2. Notice we have a nice cancellation happening. And then the negative times the positive is going to give me negative. But the I times the I is going to give me I squared. And then the square root of 2 times the square root of 2, again, we can do as square root of 4, bringing them under a common radical because 2 times 2 is 4. So this is a very ugly numerator and a very ugly denominator, but it's what we have to do. So then, what do? We say we have 36 in the numerator. These are like terms. 6I root 2, 6I root 2, they're like terms. Negative 6 minus 6, you all know, is negative 12. And then we have to carry the I root 2 along. Now, plus I squared is negative 1, and the square root of 2, square root of 4 is 2. So that just turns into a number at the end. Here we have a 36 in the bottom, but this term subtracts with this term going away. So then we have a minus sign. I times I is negative 1, and then the square root of 4 again is 2. So finally, what do we have in the numerator? 36 minus 12 times I times root of 2. This becomes minus 2. And then on the bottom, you have a 36. Negative times negative is positive. You get a plus 2. So then what we have is 36. We do the real numbers. We add the real numbers. 36 minus 2 is 34. Minus 12I root 2. And on the bottom, what do we have? 36 plus 2 is 38. So we're close to the answer. Let me just catch up and make sure I've got everything correct so far. Everything looks fine. Okay, a couple things. We want to break up this complex number, right? But we also notice that we have this divisible by 2, this divisible by 2, and this divisible by 2. So we suspect that we can simplify. So the way to do it, the easiest way to not make any mistakes is to try to factor out as much as you can from that guy. So let's factor out a 2 from the top. 2 times 17 is 34, and 2 times 6 is 12, so it would be 6I root 2. And then on the bottom, you're still going to have your 38. But now that we factored out the 2, we can say, okay, 2 divided by 2 is 1, 38 divided by 2 is going to give me 19. Because, 20 times 2 is 40, so 19 times 2 is going to give me the 38. So then, after I've done the cancellation, I'm left with 17 minus 6I root 2 over 19. And I can see there's no common factors or anything I can do there, so now I'm just going to break it apart. I have 17 over 19. The minus sign comes from here. 6I root 2 over 19, and the way I'm going to write it is 6 root 2 over 19. I'm going to write the I at the end. So the way that you would write it would be 6I root 2 over 19, but we want to write the I at the end so that we can see the real part is this and the imaginary part is this. This is the number. So you can say that I can float up here if you want, but really we want to write it as a real part plus an imaginary part. So we have 17 over 19 minus 6 times the square root of 2 over 19 times I. This is what you would write, and this is how you would plot it. Real part, imaginary part, if you wanted to plot that on the complex plane. Now, even though this was difficult, it's actually the same exact process we did before. The only reason it took a little longer is because we had FOIL on the top, FOIL on the bottom, and we had all the radicals to deal with. So that's really all it boils down to. Next problem is, I wouldn't say any harder, but let's just tackle it one step at a time. -3 plus I times the square root of 5 over -3 minus I times the square root of 5. And we want to divide these complex numbers. So we're going to have to multiply by the conjugate. So let's just write it out. -3 plus I root 5 over -3 minus I root 5. And in order to do this, we're going to have to multiply by 1, but we'll do it in the form of a complex conjugate of the bottom. -3 plus I root 5 over -3 plus I root 5, like this. So we're multiplying by 1. And we have FOIL going on when we multiply the tops and on the bottoms. And so we just have to take that one step at a time. So here we have the first terms. -3 times -3 is positive 9. Inside terms, -3 times the I root 5 is going to be -3I root 5. Outside terms, -3 times the I root 5 again gives me -3I root 5. And on the last terms, the I times I is I squared. And square root of 5 times the square root of 5, I'm going to write it as a square root of 25. Bring them under one radical, 5 times 5 being under the radical, 25. And on the bottom, similar story, -3 times -3, positive 9. Inside term, -3 times -I root 5, negative times negative is positive, 3I root 5. Outside terms, -3 times positive is going to give me a -3I root 5. We can see our cancellation happening here. And then we have, for our last terms, negative times positive is negative, I times I is I squared, and then the square root of 5 times the square root of 5, we can bring it under one radical, being square root of 25. All right, now that we have all that down, we can do the simplification, and we're basically done with the hard part, I think. We have 9. This is a like term with this. It's -3 minus 3, so it's -6I root 5. They're like terms. Then this becomes a -1, so write it as -1. The square root of 25 becomes a 5. We'll handle the simplification in the next step. Now we have a 9, but this goes to 0, so there's nothing to do there. We have a minus sign. The I squared becomes -1, and the square root of 25 becomes a 5. All right? So what we have then is 9 minus 6I root 5. Then we have a minus 5 now at the end. And on the bottom, we have 9 plus 5. And in the last few steps here, we have, what is 9 minus 5? We can do the real parts. 9 minus 5, of course, is 4. And then we have the minus 6I root 5. In the bottom, 9 plus 5, of course, is 14. So what we're going to have is, let me just double check, 4 minus 6I root 5 over 14. Okay, so we want to break it up, but we see we have a 4, a 6, and a 14. So we suspect that we can simplify it by factoring. So let's factor out a 2 from the top. And so if we factor out a 2, 2 times 2 is going to give me 4. Minus sign from here. 2 times 3 is going to give me 6, so it's 3I root 5. Double check that when you go back, you get the 4, you get the minus 6I root 5. And on the bottom, you're going to have the 14. Now that you have the 2 pulled out, you can say 2 divided by 2 is 1, 14 divided by 2 is 7. So then getting closer to the answer, what you're going to have is 2 minus 3I root 5 over 7. And now that you've done all the simplification you want to break this up into a real and imaginary part. So what you can say is 2/7 minus sign from here. And then let's write it on the top as 3 times I times root 5 over 7. Notice that if I go backwards, I have a common denominator of 7. then numerator minus numerator is exactly what I have if I were to add the fraction. So I was splitting it up just the same as I would put it together. And this is fine, but I want to bring this I down because, you know, multiplying by I is the same thing as bringing it in on the top. So it's going to be written more like a traditional complex number. Minus 3 root 5 over 7 times the number I. So this is the final answer, 2/7 minus 3 root 5 over 7 times I. And that's the final answer. So far what we've done is just taken a complex number and divided by another complex number. I can continue working problems like that, but ultimately they're all going to be the same, and that's fine. There's nothing wrong with practice. But I want to move on to a slightly different kind of problem. We've all dealt with functions up till now. Function is like a mathematical machine, right? It has a calculational machine. It's a box. Think of a function as a box. I stick numbers in the box. The box calculates something like, let's say f of x equals x squared. It squares the input, and then output comes the outside answer. We call it f of x. All right. So far, functions that we've been dealing with have only been dealing with real numbers coming in, real numbers coming out. But here's your first taste of a broader picture. Functions can operate on, as you know, negative numbers, positive numbers, decimals, fractions. But functions can also operate on complex numbers. So if you ever stick a complex number into that machine, just operate on it like usual, and then the output that you get in general will be another complex number. So you can totally have functions that operate on complex numbers. In fact, as you get higher up into math, you know, at the college level, you will take entire classes on, entire courses on complex functions that deal with complex functions in the complex plane. It's a class that lots of different people, depending on your studies, you have to take. But the basic idea is, you know, we've learned about functions. Let's take a function here, f of x equals x plus 1 over x. And you know what to do if you put the number 1 in here. You just say 1 plus 1 over 1. Or if you put the number 5 in here, then the machine says 5 plus 1 over 5. I mean, you know how to do that. But now what we're going to do is we're going to say, what happens if I want to calculate f evaluated at 1 plus 3i? So instead of putting 1 or 2 or 5, I'm going to stick this complex number in here. So all I do is I take the complex number and I put it here, and I take the complex number and I put it here. And now that you know how to divide complex numbers, you know how to do that. So what we're going to do is we'll say this is going to be equal to 1 plus 3i. That's going to be here. And then we're going to put it in the machine, in the function, 1 plus 3i on the bottom. Now, before now, you wouldn't know what to do. And there's actually a couple of ways you can proceed, actually. But the way I'm going to do it is, let's do this division first. We now know how to do that. And then whatever we get at the end of it, we're going to add it to this. Because we should get a complex number out of this that we know how to add complex numbers. So let's do that first, and then we'll add it to that. All right, so let's go off and I'm going to do a little squiggly line to tell you that I'm only working on that for right now. All right, so I'm going to say 1 over 3 plus, I'm sorry, not 3 plus, 1 over 1 plus 3i equals 1 over 1 plus 3i multiplied by the conjugate of the bottom, because I have to get rid of that. So it's 1 minus 3i, 1 minus 3i. That's what we did all in the last few problems. So now we have to multiply the tops. This is very easy because it's 1 times this, so it's just 1 minus 3i on the top. But on the bottom, we have to do FOIL. We have 1 times 1 is 1. Inside terms, 1 times the 3i is going to give me 3i. 1 times the negative 3i is negative 3i. See our cancellation shaping up. And then negative times positive is negative. 3 times 3 is 9, and I times I is I squared. And then we can simplify 1 minus 3i here. On the bottom, we'll have a 1. This goes to 0. So we have a minus sign, 9, and then we have I squared gives us negative 1. So now what we have over here on the top is 1 minus 3i, and on the bottom 1 plus 9, which you know is 10. So we've done this division here, and we got down to this point. Now we have a couple of options, and I might even do it both ways, I'm not sure. But one way we could do it is we could split this up like we always do, 1/10 minus 3/10 I. That would be a real and imaginary part. We could take that and then we could add it to this over here. That's totally fine, we can do that. Or we can take it as it is and put it in here and try to simplify it that way. So let's do it both ways, actually, just to get practice. But let's do it this way. Let's take what we got and let's stick it back to where we got it from. 1 plus 3i. Let's wrap parentheses around it. Plus, what do we get here? 1 minus, well, let's write it as a proper fraction. Let's do it as 1 minus 3i over 10. So you see what we have, 1 plus 3i, 1 minus 3i over 10. So even though it looks complicated, ultimately at the end of the day is you have something plus something, but this is a fraction. It's over 10, and this is over 1. So just like any fraction, if you have something over 1 and something over 10, the only way you can add them together is to get a common denominator. You cannot add these directly because this is over 10 and this is over 1. So it's easy to get a common denominator in this case because we can just do it like this. We could say 1 plus 3i, we can make it over 1 because it is over 1. We can multiply it by 10 over 10. And then it'll be 1 minus 3i over 10. You see what I'm doing? I'm multiplying the first one by basically by 1 to get me a common denominator of 10 so that I can add it to that. So when I multiply by 10 on the top, it gets distributed into each term. So 10 times the 1 gives me 10. 10 times the 3i is 30i. And on the bottom, you're going to have this 10, 1 times 10. But we're adding to that 1 minus 3i also over 10. Now you can see how to add it because I have a common denominator. So it's going to be over 10, and I'm going to take this numerator plus this one. So it'll be 10 plus 30i plus this one, 1 minus 3i, and I have to add them all together. And it's very simple to see how to do it now. 10 plus 1 is 11, 30i minus 3. So 30 minus 3 is minus 27, I'm sorry, positive 27i over 10. Let me just catch up with myself. So the answer that we get out of all of that is 11 plus 27i over 10, which we can then break up because we have no common factors here, so we can just break it up and say that that's going to be 11 over 10 plus 27 over 10 times I. So the answer is 11 over 10 plus 27 over 10 times I. It's a crazy looking complex number, but it has a real and imaginary part, which happen to be fractionals, and so that's the correct answer. Now I want to go back because I like to, when I can, show you different ways of doing things, and this is, I think, a good place here. We took the output of this guy, we did the math, we took the answer, which wasn't really fully simplified, we put it back in, and we finished the problem by getting a common denominator. I want to do it slightly different for you, all right? Let's continue simplifying this down into a real and imaginary part. So we have 1 minus 3i over 10. If I had to break these up, it would be 1/10 minus 3/10 times I, right? That's what would happen if I had to do that. And then if I take this complex number and put it back into there, I'm going to have to do it, unfortunately, down here. It would be 1 plus 3i, that was what we had in the first part of the function, plus this guy here, plus 1/10 minus 3/10 times I. So you see what we have here? We're going to end up adding the real parts. We're going to add up adding the imaginary parts, but we can't add them because 1/10 plus 1, I have to get a common denominator, and then 3 minus the 3/10 I or whatever, I have to get another common denominator. So just to make it clear, we're going to have a 1 here, right? And I'm going to multiply to get a common denominator, 10 over 10. And then over here, for the 3i, I can, well, that's 3i over 1. I can multiply, again, to get a common denominator with this one, again, by 10 over 10. And then I'm going to basically have all of this guy plus 1/10 minus 3/10 I. You see, you're doing exactly the same thing as we did before, and this is why I'm showing you this. But if you were to get it down like this, what you would have here, this would be 10 over 10. So you would have, well, let's just go ahead and do it full out. 10 over 10 plus, this is 30i over 10. That's that number. And you're going to add to it 1/10 minus 3/10 I. Now, you see what's going to happen here? When you add the real parts, you're going to get 11 over 10. And for the imaginary parts, the 30 minus the 3 is going to give you 27 over 10. So what you're going to have is 11/10, and then you're going to have 30 minus 3 is 27 over 10 I. So you add the real parts to get the real part of the answer, the imaginary parts to get the imaginary part of the answer, and you get the same thing. So a lot of students aren't sure, like, well, what do I do? Do I get it to a fully baked, separated complex number form, or can I just stop? And I did it a different way initially on my paper. Just take this, put it in there, and totally simplified differently, but ultimately gets you to the same place. Last problem, we're going to take this function that can operate on complex numbers, and it'll be more complicated. F of x equals x minus 1 over x plus 1. And we want to find evaluate this function when f is evaluated at 1 plus I times the square root of 3. So not only do we have a more complicated function, but when I'm plugging into that a complex number that is a real and imaginary part, but also has a radical. So it's just not very pretty. But you have to do the same thing as always. You take this complex number, you put it into x, take the same complex number, put it into x down here, and then you have to crank through that work. So putting it into the first spot, you have 1 plus I times root 3 minus the 1 from there. And then on the bottom, you have 1 plus I root 3 plus the 1 from here. But on the top, you add the real parts, 1 minus 1 giving you 0. So really all you have on the top is I times the square root of 3. On the bottom, you have 1 plus 1 is 2. Then you have plus I square root of 3. So this problem reduces to simplifying or doing that division. So how do you do that? Well, let's rewrite it. I root 3 over 2 plus I root 3. And then in order to get rid of that imaginary number, we multiply by the conjugate. So 2 minus I root 3 over 2 minus I root 3. So we multiply by the conjugate. And so then we have to crank through the math, the multiplication, which is a pain, I agree. So you have this number multiplied by this binomial. So it has this whole thing has to get multiplied by 2 and then multiplied by this term. So times the 2 means you're going to have a 2I root 3. Then multiplied by this, you're going to have a negative because negative times positive is negative. And then the I times the I is going to give you I squared. And then the square root of 3 times the square root of 3, I'm going to write it as the square root of 9, bringing them under one radical. 3 times 3 is 9. Make sure you understand that. Okay? And then what we're going to have, we have to do FOIL on the bottom. See, we don't have to do FOIL on the top because it's just one thing times this, so we just distribute it in. But on the bottom, we have FOIL. 2 times 2 is 4. Inside terms, 2I root 3. Here we have 2 times the negative, so negative 2I root 3. And then the last term, negative times positive is negative. I times I is I squared. Root 3 times root 3, I'm going to write it as root 3 times 3, which is 9, and that's all in the bottom. All right, so then we can simplify this numerator significantly. 2 times I times root 3, negative, I squared is negative 1, but then the square root of 9 is 3. On the bottom, we have 4. Now we have a cancellation. 2I root 3, 2I root 3, they're subtracted, goes away. Then we have a minus sign. I squared negative 1, square root of 9 is 3. Now we have lots of nice little numbers. Everything's looking a lot better. We have 2I root 3. Negative times negative is positive 3. Over, on the bottom, 4 plus 3. So let's write it as 4 plus 3. All right, now everything's looking good, but on the top, we have the imaginary part and then the real part. We want to flip that around so that we have the real part first, 3 plus, then we have the imaginary part, 2I root 3. That's the imaginary number on the top. And then 4 plus 3 is 7. So we're basically done, but we need to split it apart into the real and imaginary parts. We can't really factor with 2, 3, and 7, so we just split it up. 3/7 plus sign from here. Then the 2 root 3 over 7, 2 root 3 over 7 times the I, like this. And this is going to be the final answer. 3/7 plus 2 root 3 over 7 times I. That's the final answer. Pretty complicated. But I wanted to do a couple of problems like that to kind of give you a little bit of a taste of a preview. First, we started the lesson with learning how to divide these complex numbers, which basically ends up being multiplying by the conjugate. And we simplified all of that. We did a lot of practice with that. And then we kind of talked about the idea that you can have functions of a variable, but those variables can take on more than real numbers. They can take on complex numbers. And so this is just a taste, but as a preview, as you get on into math beyond calculus and even more advanced than calculus at the college level, you'll have entire classes where we study functions in the complex plane, functions of complex variables. We also call it complex function theory. It's a modern area of math that is useful in modern problems, right? So the stuff you're learning at this level is not stuff that you can just flush and say, well, I'll never use it again. If you go into any branch of science or engineering, you will use this stuff going down the road. So we have done a tremendous amount of work in these lessons here. We started out by talking about radicals and radical expressions. We talked about square roots and solving simple square root equations. and cube roots and fourth roots and things like that. And then we learned about how we can solve radical equations, equations that have radicals in them. And so we learned how to square both sides and how to simplify all of that. And then we came back to the beginning where we said we cannot take the square root of a negative number, which is a little bit of a lie at first, because in order to do it, we really have to invent a new kind of number, which is called an imaginary number. So we talked about imaginary numbers, how to multiply them, how to divide them, how to add them. And then we expanded that even further and said, hey, there's something even more general than an imaginary number. We call it a complex number, which means it has a real part and an imaginary part in the same number. It has just two different aspects of these realms, so to speak, real and imaginary. And we talked about how you can take those numbers and you can plot them in kind of an XY plane, but a real axis and an imaginary axis is what we use to represent those complex numbers. And so then we finally wrapped it all up by learning how to multiply and divide and add and subtract these complex numbers. Now, why do we do all that? I've been trying to tell you all the time that it's useful. Of course it's useful. But the reason we introduce it is because in the next set of lessons, we're going to be going back to learning a little bit more detailed about quadratic functions. Because we're going to learn that sometimes when we solve quadratic equations, we're going to get complex numbers as an answer. We have solved some quadratic equations before now, but those were carefully chosen so that they just gave you real numbers. And when I say quadratic, I mean x squared plus 2x plus 5 equals 0. We're going to solve equations like that. But we're going to find that in the more general cases, we're going to have complex numbers as an answer. So we had to introduce complex numbers in order to understand that. So make sure you understand everything in this unit of lessons. Solve all of these problems. Follow me on to the next unit where we'll go back to the quadratic functions and we'll learn that some of those solutions actually end up being complex numbers, which we've learned here. Learn anything at mathandscience.com.